Dear friends and colleagues, thanks very much for being here. This seminar on our space science and technology. We are organizing with the program for space engineering at UC3M. It's my pleasure to welcome Professor Ignazio Viola, who's going to be talking today about the nature, how nature flies. So it's a very inspiring talk. Thanks very much for being with us, Ignacio. Ignazio Viola is reader. He's an associate professor at the School of Engineering of the University of Edinburgh, and is a fellow of the Royal Institute of Naval Architects. His research group, the Vortex Interaction Lab, VOILAB, focuses on how vertical flow structures interact with wings, blades, and sails. Vortex-dominated flow is frequent in nature, which is a key source of inspiration for his research, and he's going to be talking about us today. Ignacio has written more than 100 peer-reviewed conference and journal articles, for which he has been awarded 2 medals of distinction and 1 medal of exceptional merit by the Royal Institution of Naval Architects. He has contributed to securing research grants for more than 15 million pounds, and he's currently PI or leading an ERC consolidator grant project on Dandelion inspired fires, and also an engineering and physical science research council project on the inspired morphing blades for TDL turbines. You have links to these 2 projects and to his lab in the website, as well as an abstract of the talk, a couple of featured articles in his bio in the web of the PhD in aerospace engineering. So again, thank you, Maria, for being here. Ignacio, Maria, for being here. I give you the floor, and please go ahead whenever you're ready. So
thank you. So thank you very much for having me here. If you ever wonder how nature flies, have you ever been asked by some of your colleagues, how do, for example, a bird fly? I'm sure you have. We all have been, and we all have probably given very different answers. Yet probably we do understand the underlying physics, and we have some common knowledge of how does it work. And we probably would all say that the wings are important because the force will be proportionate to the area of the wing, and also to the dynamic pressure, of course. Yet we have also learned that this is not the only way to fly, because, for example, you might be familiar with the bumblebee paradox. The bumblebee paradox is such that if you consider the principle that the forces must be proportionate to the area of the wing, then the bumblebee does not have enough wing area to generate the forces to fly. So there must be something behind it that will allow the bumblebee to fly in a different way compared to, for example, this beautiful albatross. And the way was actually discovered by Ellington in 1996, and then followed up by many researchers, who actually showed that there is a leading edge vortex, which is a vertical structure generated at the leading edge of the wing, which fundamentally replaces the vorticity that otherwise would have been at the boundary layer of the wing. And in this way, we have identified a new way of flying. This is not just insects that exploit the leading edge vortex, but there are also seeds. Seeds should not be underestimated, because seeds can fly as efficiently or more efficiently, in depending on which one is the index we use to define efficiency, as insects. Surely insects have more control of where they go compared to seeds, but seeds are very efficient flyers. And in fact, for example, the maple seed, in this beautiful visualization by Lentig and Dickinson and co-authors, actually shows that even the maple seed exploits the leading edge vortex to enhance the lift, and therefore to exploit a different way compared to the albatross for flying. So now we have learned that we still need a wing. We still need a wing that might not have all the surface that we wanted, but still an impermeable wing can generate the force we need to fly. Then how does this one fly? You know, this one fundamentally does not have a wing, and this one does not have a wing as well, and yet they fly very, very efficiently. So here, there must be something behind it, because if we look into the wings of these two objects in front of us, we don't see fundamentally any area either to generate lift in a traditional way, either to generate a leading edge vortex. So what's the way? Is there a third way to fly, perhaps? So what I'm trying to do today is to show you some of the things I have learned about the flight of the dandelion fruit, which by no means is the full story. I only know just a little bit. I will raise some questions and I will give you very few answers. Then I hope in the future years, maybe some of you will help me to find the remaining answers. If you look, for example, at this dandelion fruit in a wind tunnel, what you can see here is that the seed do not fall as we expect them to do. For example, this seed that you might see now just in front of your screen is just there, steady behind the fruit, and is not falling at all. How does that happen? Well, look, if you consider that these seed are taking off from just 10 centimeters as an order of magnitude from the floor, instead of landing just under the fruit, they land at 1 meter from it. This is quite extraordinary. They land 1 meter away from the fruit. In fact, 99% of the seed will fall within 2 meters from the original fruit. But even more extraordinary is the fact that some of these seeds, some of them, which is what really makes the plant extraordinarily efficient in dispersion, some of them, they can travel hundreds of kilometers. Imagine dandelion in your garden that goes to the beach in Barcelona, just transported by the wind. Isn't that extraordinary? But it does happen, and it happens every day. So let's have a look a little bit more in details into the dandelion. How does it look like? Well, this is a picture that we took of it. You can see that it does have these filaments that open up and then has a very, very thin, with fundamentally a negligible mass that connect this wing on the top to the seed on the bottom. And all of the mass is in the seed. If you look at it from the top, you see this wing, which is fundamentally empty. It's fundamentally empty because if you take that picture from the top on the right-hand side of the screen, what actually happened is that you compute how much is the area of that disk and how much is the area occupied by the filaments in that disk. You figure it out that only 10% of the area is full. Everything else is empty. Only 10% of the area is occupied. It means that it's a 90% porous wing. If we do some drop tests, so for example, you can take these seeds and you can put them into a container or in a room where the air is not moving at all, it's completely stationary. You drop this seed, you will find out, first of all, that the seed have a comparatively very large mass. Actually, 0.6 milligram is quite a lot of mass if you consider that they fall only at 0.4 millisecond. The filaments you see, they're only 16 microns, but the pappus diameter is 15 millimeters. What it means that there are two very different length scales. There is a difference of 2 orders of magnitude between the two. And there is the length scale of the filament, and at 0.4 meter per second, that will give you a Reynolds number, which is below 1. So that would be Stokes flow. Or there is the length scale of the pappus, which is 15 millimeters, and at 0.4 meter per second, that will give you a Reynolds number of 400, which is quite a high Reynolds number if you consider that at Reynolds 400, you have all the features that you normally would expect in terms of the turbulent von Karman waves and so forth. So if we try to imagine how, if we try to study how this seed can generate the force that it needs to fall so slowly, despite of the heavy weight it has, well, the first consideration we should make is try to sit on top of one of the filaments and look how far the other filaments are. So for example, you can sit in the middle of one of these filaments, sometimes in between the center of the seed and the end of the disc. You look around and you see that the next filament is more than 10 diameters away from where you are. 10 diameters is quite a reasonable number. You would expect that the other filaments has very little interaction with what is the flow around one filament. And with this approach, if you consider this to be acceptable, you can compute the force around one filament. It means that the flow will simply be Stokes flow. It means that the flow will not separate around the filament, it will just go around it. And we can use some analytical formulation, we can estimate the force. But if you do that, you only find half of the force. You find that the force generated by 100 filaments is only half of the force that you need to fall at 0.4 meter per second with a mass of 0.6 gram. So that is not the full story. It's only half of the story. There is something else going on. Something else that actually is the reason why the dandelion can fly so far away, and because it falls so slowly. Let's investigate this. Let's take a dandelion and let's place it in a wind tunnel. This time we place it in a vertical wind tunnel, such that the flow comes from the bottom and the dandelion is actually steady because the flow is flowing exactly at 0.4 meter per second, at the velocity at which the dandelion will fall in steady air. And what we see is this. We see that the flow goes around the dandelion, and then some of the flow goes through the filament and form a vortex ring. This is quite extraordinary. The reason why it is extraordinary is because this one is a steady flow, and a steady flow for the flow past a disk at a Reynolds number of the order of few hundreds, it's normally not what it does happen. You would expect vortex shedding, but instead you have this long exposure picture that shows pretty well what is the steady flow around a dandelion. Now, in order to investigate what is it that enables the dandelion to achieve a steady flow in the wake instead of an unsteady flow, well, first of all, let's compare with a disc which has the same diameter as the pappus of the dandelion. The pappus is this filamentous wing. Let's compare the dandelion with a solid impervious disc at the same Reynolds number. More precisely, let's make the disc of the same diameter, let's flow it in air in the same wind tunnel, and let's flow it at the same velocity. What we find is this. Now, you might not believe me if I tell you that this is exactly the same Reynolds number. It looks to me that the flow is flowing so much faster behind this disc than behind the dandelion, but it's not. It's not. The truth is that only the flow inside the wake has a different velocity. Otherwise, the flow velocity is actually the same. So this is the same Reynolds number. And you see which tremendous stabilization effect the dandelion manages to achieve through this particular geometry that it that it exploits. Now, we don't know yet if what makes this ability is the permeability of the wing or the particular geometric structure of the filaments, or maybe the fact that the filaments are not actually a flat wing, but is a three-dimensional wing with some angles. You see, some of the filaments points upwards, some of the filaments are more horizontal. So one of the things we could do to investigate is to manufacture a small artificial dandelion which has these filaments such that we achieve the same number of filaments, the same porosity, so the same ratio between the full area and the area effectively occupied by the filaments and the center. And this ratio, as I said, is 0.9, which means 0.9 is the porosity of this disc, exactly the same porosity as a dandelion, but we don't have any other effects. For example, the fact that some of the filaments are pointing upwards or downwards. All the filaments here are flat. And here is what we find. The picture in the middle, the video in the middle, is the filamentous disc, again, precisely at the same Reynolds number. So what we have shown here is that it's true that if we have a filamentous porous disc, we can stabilize the wake. Now, why is that so important? Well, without going too much into the details, you will certainly realize that if you want to fall as slowly as you can, you not only want to maximize your drag, but also you want to have a stable position, which is the position where your drag is maximal. You don't want to start tumbling, because if you tumble, there will be time where you will fall much faster. And so on average, you will touch probably the ground sooner. So this is the first very smart thing that nature has taught us, is that if we have a filamentous, highly porous wing, we can stabilize the wake. But this is not all of the story, because we still do not know if this stable wake is actually allowing you to have a force which is strong enough to support your weight. Maybe a solid disc would have provided an unstable but on average higher force. So let's investigate this. Well, before doing this, we need to do one more thing, which is to understand how much do we really need to have a filamentous structure rather than just a porous structure. If we have a porous disc, actually a uniformly permeable disc, do we achieve the same results, or do we need filaments? Are filaments really important, or we simply need to have a highly permeable disc? The answer is, if you run numerical simulations where you can have a virtually very permeable disc without having any consideration for the structure, because artificially you have imposed the sign permeability, you do find this separated vortex ring. So that means that filaments are not important. What it is important is the permeability. But also CFD simulations allow us to look into the pressure field, which would have been difficult to measure experimentally. And the pressure field reveals a little bit of the underlying physics here. You can clearly see that, as often happens in steady vortices, at the center of the vortex, there is a minimum pressure. So the flow is effectively rotating around a ring of low pressure. And this overall makes the separated vortex ring as a flow feature which is characterized by low pressure, which is that low pressure that generates the force that is actually the drag experienced by the disc. Now, if this one was an impervious disk, you would see a very similar picture, if not that the flow would have been unsteady instead of steady. We can also look into the vorticity, which is particularly interesting because it reveals a little bit more about how these forces can be generated. Here you see, if you look into the vorticity, what you observe is that even if you can see streamlines passing through the disk, actually the vorticity is generated in the shear layer at the edge of the disk. There is not really vorticity which is convected through the disk and put into the wake. The vorticity is really generated as if the disk was impermeable at the edges, and then it is shed into the wake. Now, what is the real difference here between the impervious and the permeable disk? Well, the real difference are the streamlines that go through the disk. So let's try to exaggerate and see what does it happen if we increase the permeability. What does it happen to this separated vortex ring? What does it happen to these streamlines? And here is the case where you see from the left to right a gradual increase in permeability. Here we measure permeability by the Darcy number, and the Darcy number in this case ranges from 10 to the power of minus 4 to 4 times as much, 10 to the power of minus 4. You can see that in all of these cases, the wake is really much generated by vorticity at the edges of the disk. And what you see is that the higher the permeability, the more is the flow rate through the disk, which what it does is to displace the vortex farther downstream. Now, this is very interesting, but what does it tell us in terms of forces? Which is the optimum permeability that you would choose if you were the Dandelion in order to fall as slowly as you can? Perhaps they're just the one you need to stabilize the wake, but you don't want to go any farther. Or maybe instead there is a permeability where the force is even higher than if the disk was impermeable. Well, this last possibility is very unlikely, isn't it? Would you expect that you have a wing, you put some holes into it, and that would generate even more force? That's unlikely, isn't it? Yet, this vorticity distribution in front of you actually provides you some hint. You can see that what the separated vortex ring can do is to somehow modify the mixing of the vorticity in the wake. And even if on the left-hand side there is clearly higher region of darker color suggesting that more vorticity is generated, yet in the picture in the middle you can see that the wake extends farther downstream, and you can see longer edges of these orangey color plots, suggesting that effectively in the wake the moment of vorticity, which is indeed the drag, could be higher. Likely for us, we don't need to compute the moment of vorticity. We can directly compute the delta pressure across the disk, and we can numerically do some experiments and verify how does the drag force, or the drag coefficient if you like, vary by increasing the permeability, or the Darcy number, of the disk. And this is what we find. Now, very surprisingly, from my point of view, is that if you take one of these curves, each of them represents a different Reynolds number from 10 to 30 to 130. If you take any one of these curves, on the left-hand side, you have a very low Darcy number, which means that you have an impermeable disk. This impermeable disk has a constant value of force, and if you start putting holes through the disk, you will move along the curves from left to right. At the beginning, you put some holes and nothing really changes, but then, surprisingly, the force begins to increase. It increases up to a maximal, and then it drops very quickly. And eventually, if you have too many holes, up to the point that your wing is almost disappear, then the force goes to zero. So it looks like, taken from this plot, it looks like, first of all, that the Reynolds number matter, but don't fool ourselves here. If you go much higher than 130 in terms of the Reynolds number, the curves do not change anymore. So the curve at 130 would be very similar to the one at 230, 330, 430, because all they are actually collapsing towards an asymptote, which is very close to that curve. So we plot 130 because we could have plot all the other numbers. We will only be pretty much on the same point. But what it looks from here is that there is optimum Darcy number between 10 to the power of minus 4 and 10 to the power of minus 3. So if you were the Dandelion, that's where you would like to be, isn't it? You would like to try to be precisely there, where you maximize the force and therefore you slow down your descent. Now, the other part of the story is, however, that we should not forget that we still need to be safe in terms of stability. So is that Darcy number enough, the one that maximizes the force, is that enough to make your wake stable? Well, this is very important, right? But also, you would like to carry the maximum weight as you can, which means that you want to be sure that the heavier the weight, the more faster you will fall, the higher the Reynolds number. Yet, you always want to have that in terms of coefficients, you remain as efficient as you can be, the maximum force. Therefore, you want to have that Darcy number. Now, the question is, can you go higher in terms of Reynolds number? Can you carry more loads, remain stable, and keep the same permeability? So in other words, what we have to do here is we have to compare this plot where we know we want to be a Darcy number 10 to the power minus 3, 10 to the power minus 4, with this plot where we actually want to be sure that we stay on the steady side of the plot. If we cross the line that is on this plot, the wake becomes unstable. As you can see, the porosity, which is on the horizontal axis, is very important in stabilize the wake. If you have zero porosity, like the albatross, for example, just when you go above a Reynolds number of 150, you become unstable. So that will not be a physical, meaningful way for the albatross to fly. But if you can increase the porosity, then the Reynolds number goes up. Now we said the Dandelion, in terms of the pappus, has a Reynolds number of the order of 400. In order to achieve a stable wake, in order to be able to fly at Reynolds number 400 and to carry that weight, the porosity has to increase above 0.9. And look how remarkable that pink dot on the top right of this plot represents where the Dandelion really sits. That one is that pink dot with its own arrow bars represents the critical Reynolds number at which the wake behind the Dandelion will become unstable if you were increasing the weight of the Dandelion, and therefore if you were making it fall faster and faster, increasing the Reynolds number. So it's quite remarkable that the Dandelion is capable to pick the optimum Darcy number, the optimum permeability, but also the optimum porosity to ensure that actually its wake is just enough to be stable. Now you can see this curve. You may wonder, where does it go? And someone else has wondered as well, and this is the work of Leda and co-authors at EPFL. They show that these two curves do not match perfectly, but what the curve from Leda show is that there is a stability of the flow that becomes asymptotic at the porosity 0.93. So they did linear stability analysis, and what they found is that if the porosity is as high as 0.93, you can go high in the Reynolds number and the flow will remain stable. Now, differences between these two curves are probably due to some differences into the geometry that they tested, even if it was undesirable. But they tested circular filaments, where the experiments that we perform, which are the rounded dots here, they were based on the artificial dandelion that we made, where the filaments were rectangular. Anyway, what this really shows is that the dandelion is so smart to actually fit precisely on this line of marginal stability, and even more remarkable, if these are all the yellow dots, are all the dandelions that we have tested in our wind tunnel, and they all flow. This one is a zoom in region of what is near that pink dot. They all flow very, very close to the curve that will make their wake unstable. If they, in other words, if they had just a little bit more filaments, they would not have enough porosity to sit on the right hand side of that curve. And if their seed would have been just a little bit heavier than what it was, they would have not allowed those yellow dots to be under that line of stability. That's how smart the dandelion is. So in conclusions, what we have learned is that perhaps there is not only one way to fly, which is the one of the albatross, of two. Sorry about this. Or two, which is how the leading edge vortex allows, for example, insects to fly. But perhaps there is a third way, which is the enhanced force enabled by the separated vortex ring. We have also learned that there is something similar to a natural optimum permeability that will allow a wing to maximize the force that it generates. And now remember that even if that little increase in drag might look small to you, remember that every time you make your wing more permeable, you're also saving in terms of weight. So the increase in terms of efficiency is way higher than just increase in the force. And finally, we have learned that in terms of porosity, there is a vertical asymptote to the stability of the flow, such that you need to be enough porous to ensure that you have a steady wake. Now, in the last minute of the presentation, I would like to show you some of the idea that came up from this research. 20 years ago, way before we started this work, it was developed this technology that is called smart dust. This is a little mole, 1 millimeter cube, that can be dropped by an airplane, and it falls, takes a few minutes, for example, of the order of 15 minutes, to fall on the ground, but during the flight, it's capable to record information and also to transmit information. Nowadays, within that millimeter cube mold, it is actually possible also to fit a camera. Now, this technology is not very common nowadays, but yet it does exist, it is in use, and it works. Now, the unfortunately is that you don't really control where it goes, and more importantly, it only stays in the air for a few minutes. So for that reason, there is a strong push to try to develop insect-inspired drones. This is a 5 mm drone, or 1 centimeter drone, if you like, which is known as RoboBee, and yet because it has to flap the wings, it consumes so much power that has to carry a battery which is so heavy that eventually does not allow this drone to fly for more than a few minutes. In fact, it's not even yet been able to fly for a few minutes, but certainly it will be in the next few years. But what if instead of taking inspiration from insects, we take inspiration from seeds? What if we could actually develop a technology which would be able to carry the mole of the similar to the smart dust for hundreds of kilometers and remain in the air for days instead of only a few minutes? Potentially, taking inspiration from seeds could increase the endurance, so the time spent in the air, by more than 3 orders of magnitude. And this is the subject of our current research in our group, funded by the ERC grant. Now, before I conclude, I just would like to acknowledge my collaborator, and particularly I would like to mention Naomi Nakayama, who has been the person who invited me at the beginning to start working on this. She is a biologist, extraordinarily good, and now unfortunately has been poached by Imperial College, where she established a very successful laboratory. Enrico Mastropaolo was my colleague at the University of Edinburgh and a very close friend who unfortunately passed away a few years ago, and he manufactured the prototypes that we have tested in the wind tunnel. And lastly, I would like to mention Hall, who is the first author of the papers that are related to this work, an extraordinarily good fluid mechanicist who has been my postdoc during this project and now is a lecturer at Harvard University. Maddy is another postdoc of us, now a fellow at Oxford. Alice is now a postdoc at Strathclyde, and Daniele is a PhD student of mine. Thank you very much, and I'll be very happy to answer any questions as far as I already know the answer about this extraordinary seed. Thank you.
Thanks very much, Ignacio, for this amazing presentation. Very inspiring, I would say. I would first of all give the floor to anyone in the audience. I know you cannot talk, but you can probably raise your hands, and don't be shy and pose a question.